Welcome, everyone. It's really great to see so many people, I guess more than 100 people on this call. MFEM has been around for a while, but we've never gathered the community like this. So this is a real thrill for us. We're hoping there will be some interesting connections made. Maybe you'll learn more about what we're doing. Maybe we will learn how to help you. If this goes well, we'll do it every year. Aaron already said it's an annual meeting. It's the first. So it really is our meeting. And, it doesn't have to be super strict and the talks don't have to be super polished. It's really about the discussion and following up. So thank you for coming. We really appreciate that. There are a lot of cool application talks that are coming up. My talk will be mostly about the past, the present, and what we see as the future of MFEM, at least in the near term. We have a lot of new people, so let me just give a very brief introduction to MFEM. Let me see. Can you see my mouse pointer also?
Yes.
Hopefully you can. All right. So MFEM is a finite element library. We've been developing it at Livermore for a while. We'll go over the history. And the idea of MFEM is that it provides cutting-edge algorithms to build powerful applications that are targeting high-performance computing architectures. This is some of the features and the project that we're part of. And this is just a partial highlight of our main features. I'd say the first one is that we try to be very flexible. You can use MFEM for research in finite element discretizations on general unstructured grids. We treat simplex meshes and tensor product meshes, so tensor product element meshes, so triangles and quads on the same level. We provide, for example, local adaptive mesh refinement for both of them. There are a wide variety of bilinear and linear forms and finite element methods that you can develop with MFEM, continuous, discontinuous Galerkin, DPG, isogeometric analysis, all sorts of things. So flexibility is very important for us. The second thing that we're emphasizing is higher the methods and scalability, large scale scalability. At Livermore, as you may know, we have big supercomputers, so that's one of our goals for sure. And when we say high order, we mean arbitrary order spaces, arbitrary order meshes. When we say scalability, we mean MPI scalable to millions, of course, and GPU acceleration. That is a very big focus for us, and it has been a focus for us for the last 3 or 4 years. We want to scale in the whole hardware spectrum, though. It is very feasible that you can start with a simple serial code in MFEM on your laptop, build it, download it, build it without any dependencies in 10 minutes. And then as you progress with small number of changes, you can turn it into a highly scalable code that then you can run on a supercomputer. And then you can even use GPU acceleration. So it's really the whole spectrum. We want to use MFEM as a tool for development and applications. There's a lot of connections with external packages. And for example, Hyper is one of the main ones. So we support a lot of solvers. There's also support for libraries that provide solvers on GPUs like AMGX. You will hear more about solvers later in the day. There are various ways to visualize our results, particularly these higher the curved meshes. As you can see, they can be very deformed. You can do it with Visit, ParaView, or our own visualization tool, GLVis. And of course, MFEM is open source. So it's BSD license, it's been on GitHub. We have a lot of examples, and we're part of things like FastMath, the ECP project, Exascale Computing project, XSDK, and others. All right, so this is a one-slide overview. Now let me go back in history. So MFEM actually has been around for a while. It started more than 20 years ago, actually as a student project in a numerical analysis class at XM University. Very few lines of code have remained from that, but that's really the origin of the project. And Vesel and me and Stan were some of the first developers there, and we used it when we came to Livermore during our summer internships. The real push behind MFEM was the BLAST project that started at Livermore around 2010, so 11 years ago. And actually, the MFEM proper repo started in May 2010. Vessel and me and Rob and Truman and many other folks joined after that. And the website went live in 2015. In the beginning, we were developing internally and just pushing the releases to GitHub. In 2017, so 4 years ago, we actually moved the whole development to GitHub. So MFEM now is being developed fully open. Everything we do is directly pushed on GitHub. And the team expanded dramatically to include many, many more people, and a lot of you, and the community grew significantly. Then another important step was in 2017, a little bit later in the year, the seed project in the exascale computing project in the United States started, and that's the project that has pushed a lot of the partial assembly, GPU acceleration, and exascale computing developments in MFEM. So MFEM is one of the two main projects in seed, along with NAC 5000. Okay, so this is the history in one slide. Now, over the years, the source code base has grown significantly. This is time, lines of code in thousands, and these are the different releases. The ones in boxes are the main releases. As you can see, the growth is, well, it's not linear. It's at least quadratic, maybe more than that. And our latest release, 4.3, is over 300,000 lines of code. These are all the releases. You can find this on our downloads page. As you can see, a steady stream of releases, all of them adding major features. Some of them, like 4.0, for example, added GPU support that are really groundbreaking. And it continues to grow, and it probably will continue to grow because it's being used in growing number of different applications. With the growth of the project and the software library, the community has also grown. Aaron already mentioned some of that. On GitHub, we have 108 contributors to the master branch. We're getting about 100 commits per week. The MFEM organization has 456 people. The last time I checked, please join that if you want to contribute. That's a requirement, actually. And also, that's a good way to receive announcements. We basically use that organization as a mailing list. We're getting about, on GitHub again, we're getting about 100 visitors per day. I think we had about 810 stars. We really appreciate those. Those actually matter for us, and when we justify MFEM in front of the management. So if you think we deserve it, please give us a star. And these are the kind of the top contributors as of October 2021. You can kind of very clearly see 2017 when we actually moved the development to MFEM and all the big spike. And you can also see that some of the top developers are actually people like John that joined the project relatively recently. So they've been extremely productive. All right, so in terms of downloads, we're getting about 35 downloads and combined downloads and clodes per day, which is about 12,000 per year, which is significant. The total number of downloads MFEM has been downloaded from more than 100 countries. And another indication of the growth of the community is this workshop. I think the last time I checked, there were 238 people registered from a wide variety of organizations and countries. Okay, so the last release we had, 4.3, came out at the end of July. And it was really a team effort. It took 9 months, 81 contributors, 218 PRs merged, 265 issues closed. If you count the number of work days in 9 months, that's actually more than 1 PR per day. About 50,000 lines of code and 4,000 commits, many new features. This is just to give you an idea of the action of people committing to different portions of the code at the same time. It was very parallel development. This is actually on YouTube if you want to take a look at the whole movie. The changelog was, I don't know, several pages with many new entries. And we're really, really thankful to all the internal and external contributors. These are all the folks on GitHub that has contributed to the code in MFEM. And we really appreciate that. So this was kind of the review of where we came from. Now I want to talk about the present and the things that are really important, that are the cornerstones of the way we help applications, of what enables us to have impact. And there are a lot of those. You highlighted the ones that are important for you during the survey. I will just highlight 3 of them, and there will be more that will be highlighted in talks later in the day. Okay, so the first one is Howard methods for large-scale multiphysics applications. The example from that is the BLAST code. Rob will have a talk on the Marble project, which includes BLAST. And BLAST is a large-scale Howard multiphysics multiphysics L code at Livermore that combines radiation diffusion, electromagnetic diffusion, and compressible hydrodynamics. This is one example of how finite elements really map well to multiphysics problems. We use the whole Durham complex in MFEM. We swear by the Durham complex. We support all spaces in it, H1, H-curl, H-diff, and L2 at the same level. And in BLAST, H1 very naturally maps to the kinematic variables. H-curl is used for the electric field in MHD. H-diff is used in the flux-based radiation diffusion, and L2 is for all thermodynamic quantities. Now, using high order for all of this enables us not just to get increased accuracy for smooth problems, but also for problems with shocks, like the ones we're considering here, to get resolution at the sub-element level, to follow the flow, to preserve symmetry better. Here are 2 examples. This is robustness, purely Lagrangian flow, where the mesh follows the physical velocity. There's a vorticity in this problem. It's a triple point shock. And so, for example, from here to here, this is one element. You can see elements being deformed here following the slip line. These are 8 order elements. And this is what we can do with MFEM and the higher basis for the full Durham complex. This is what you get if you don't do that. If you just use linear elements, the mesh tangles very quickly. And here's an example from symmetry preservation, where you have a purely spherical radial shock that everything should remain spherical in this problem. The initial conditions are spherical. And this is what you get with low order methods. You get a lot of artificial numerical distortion. This is relevant, for example, to the National Ignition Facility at Livermore. You might have heard the big laser that recently got very close to fusion. All right, so there are a lot of mathematical benefits, but with harder elements, there are also a lot of high performance computing benefits. It's really the time for them with GPUs and modern hardware coming around. And we're trying to leverage both and be a win-win, get the best from both worlds. Of course, there is a price to pay. The price is new research, high power. So these are very powerful methods, but with great power comes great responsibility. So we need to be controlling oscillations, ensuring positivity, all sorts of interesting mathematical methods from discretizations to solvers, adaptive mesh refinement, visualization. Everything needs to kind of be upgraded to high order. All right, so 5 years ago, this is where we are. This is where we were. So this was strong scaling with the BLAST code, purely MPI. This is before GPUs on BGQ, where we could scale to 131 MPI ranks with different order methods, so 2nd, 4th, 8th, and 16th, and we could strong scale to 1 element per core. This is pure refinement, where on the same mesh we increase the order. And this is what we had for the case where we keep the same number of degrees of freedom when we increase the order. So when you go to a lower order, you also refine the mesh. And as you can see here, even though we were increasing the order, we were running in the same amount of time and getting better results from the high order. Now, I must say, this is actually old, significantly old. We have improved this significantly, and I'll show you. And in fact, now when you run high order, you run faster. And also we're supporting GPUs. That's the big difference. But if you have a purely MPI, if you're interested in purely MPI simulation, this is the type of scaling that you can expect. Okay, so the first thing I wanted to talk was hierarchy method. The second thing is adaptive mesh refinement. This has been a very important enabling technology for us. In MFEM, as I mentioned, we support both conforming local refinement for simplices, including in parallel, and non-conforming refinements for quadrilateral and hex meshes where you have constrained nodes. We do have HP refinement that works in serial and in 2D in parallel, but the 3D parallel isn't currently in development, so it's not fully complete. But other than that, the AMR capability in MFEM is very general. It's done at the library level, at the finite element space level. It supports all the DRAM complex, all the spaces, 2D, 3D, hexes, prism, TETs, arbitrary order hanging nodes. There's no restriction what should happen on the coarse fine interface in terms of number of refinements. We support anisotropic refinement, derefinement, parallel load balancing, and it's independent of the physics. That's, I think, the important thing. It's done in MFEM, so any application doesn't need to reinvent the wheel. They can just run on non-conforming meshes. It's done in a very natural way. I'll point out to it in one of the following slides. And this is some of the examples that we have in the Miniapps. Let's show this. All right. So here is how this works in practice. This is the set of blast problem, which is a release of energy at the corner here that spreads radially. What you can see, it generates a shock wave, a radial shock wave on this mesh. And you can see here, refinement, derefinement. This is the parallel load balancing on 16 cores. So it works quite nicely. And this is how it scales. This is a scaling up to 3080 MPI ranks. It's one of these plots where you have both strong and weak scaling. The solid lines correspond to strong scaling, and the different sizes are picked in such a way that these dashed lines correspond to weak scaling. And so you want the solid lines to be straight and you have a straight slope, and the dashed lines to be actually horizontal. This only measures the AMR infrastructure. There's no physics here. So this just measures the construction of the interpolation, the assembly, the marking, the refinement, the rebalancing. The rebalancing here is done with the space filling curve, the Hilbert curve. So this is actually really nice. If you add the physics, it will just become better. And I think it's really reasonable for large enough sizes. You certainly strong scale really well. And in general, the weak scaling is very nice. And we have a paper on this. We have papers on a lot of this stuff. I'm just covering here the capabilities. If you're interested in the theory, you can go visit our website for the papers. Okay, the third thing I wanted to highlight, and that's the last one, is the GPU capability. I mentioned the seed project that motivated this. And the foundation for a lot of this work is the operator decomposition and the partial assembly of finite element operators. And the idea there is that any finite element operator can be split in this form. These operators are interpolation operators between the global degrees of freedom, the local degrees of freedom on each MPI rank, the degrees of freedom on each element, and the transition from element degrees of freedom to quadrature point data and the assembly back. And for higher operators, you do not want to form the whole matrix. You want to actually provide individually all of these pieces. That's how we get performance. For example, we take advantage of the tensor product structure and tensor product elements and apply B as a sequence of tensor contractions as opposed to forming it. The way we handle adaptive mesh refinement is just by changing the P and the G or the G operators. Everything else remains the same. So you are able to assemble everything that you were able to assemble before on non-conforming meshes automatically. And there's a lot of interesting research here. We're happy to follow up if you're interested. But this perspective, together with a significant refactoring in MFEM support different device backends, enables us to run really well on GPUs, and not just on GPUs. This flexible device backend structure is really future-proof for us. Anything that comes in the future, we can adjust. We now have all our main kernels very clearly separated with which kernel we say what are the input parameters in terms of read, write, or write to minimize memory transfers. And then the kernels are either lambda captures or implemented directly in one of these backends. The backends are additive. You don't have to implement everything in all backends. You can use just portions of the code and then fall back on other backends. And soon there will be Intel and SQL backend. So right now we support NVIDIA and AMD GPUs. And just as a point of reference, we've been providing GPU acceleration in an official release for over 2 years. So since MFEM 4.0. These are just some results on my desktop, actually, with the different backends. The one that are red are single core backends, the one that are green are multi-core, and the one that are blue are the GPU backends. And we have a variety of options. This is literally what you say. This is the device specification. You say example 1-D, and the string, it's one executable that can run at, you select at runtime, which device backend to use. And as you can see, for different orders, you get improvement with the order. And going from single to multi-core on this machine, it's about an order of magnitude. And from multi-core to GPU was another order of magnitude. This was one node. This is what you get when you scale it up. This is up to 1,000 GPUs, but we've scaled to more than this. This is a plot where you have a local problem size versus a local performance. And again, you see that for the same problem size, higher orders, so different colors, different orders, higher order give you better performance. That drops a little bit when you go from 1 to 4, you have some communication. But from 4 to 1,000, you pretty much stay at the same level in terms of the max performance. And here you are getting performance of 2.1 teraDOFs per second. And you're solving a 34 billion problem in a matter of minutes. If you're interested to learn more about this particular topic, I would recommend going to the SID website where there's more information about the benchmark, the Miniapps, this libseed library. This is the URL. We're heavily leveraging this in MFEM. Okay, so based on these capabilities, we are building applications. The first step for new users is to look at the example codes. We have this webpage, mfem.org/examples. The example codes have both serial and parallel version that show you how to transition. They're tutorials, and they show the integration with a lot of the external packages we have and external projects like SID and the ECP. The next step is Miniapps. We have a lot of Miniapps, but the two I wanted to highlight is the electromagnetic Miniapps, so Volta, Tesla, Maxwell, and Joule, solving a variety of electromagnetic problems, mfem.org/electromagnetics. And then the Navia Miniapp, which is the transient Navier-Stokes problems, mfem.org/fluids. There will be breakout sessions for both of this. So if this is what you're interested in, we can talk more during the breakout sessions. And then the next step is real large-scale applications, of which there are a lot. You're going to hear about a lot of those: BLAST, topology optimization, collaborations with industry, tokamak simulations for SIDAC, electric aircraft design, medical applications, and more additional applications from our SIDAC partners. And this is just a sample. One of the things we wanted to see is what do you guys do with MFEM? Okay, so now let's look a little bit into the future. So I'll start with our plans for next year. There are several major topics. The first is improvement in the GPU support. We will add parallel assembly on the GPUs and have scalable solvers for the full DRAM complex, not just for H1. And not just for NVIDIA GPUs, also for AMD and Intel GPUs. We plan to make the GPU kernels easier to write, continue to improve their performance and clean up the code. This is targeting El Capitan, the machine that we're going to get in Livermore in 2023. Then, of course, we are going to continue to add features that are motivated by the needs of our applications. And this is your chance also to chime in and tell us what you're interested in. One important one is subdomain extraction and handling different physics in different domain. User-defined variational form, better handling of nonlinear problems, being able to handle initial meshes that are very large and repartition. And then features like automatic differentiation, mixed meshes with pyramids, connections with machine learning, and reinforcement learning in particular. We have some efforts there, sharpening of interfaces and other research topics. We want to improve the code quality, the documentation, additional examples, unifying interfaces, and just generally polishing. We know we've added a lot of code, particularly on the GPU front, and it will be great to stop adding so many features and just polish a few of them. So that's one of the focus for this year. And then we plan to release 4.4 in January, so about 6 months after the current release. And I just want to give everybody a heads up. In the next major release, 5.0, it's coming soon. This is an aspirational date. July may slip, but that will probably have some breaking changes because there are some overdue fix-ups that we've been particularly with respect to memory management and ownership that we've been meaning to do, and those will require actually API changes. Okay, so this is next year. Further down the line, some of the things we're interested in are design optimization for engineering applications, cloud computing, expanding the reach of MFEM in the industry. I think we have a big potential there that's not fully realized. Additional connections with machine learning. We have several efforts there. Automatic compilation of variational form and support for just-in-time compilation. Other hardware like ARM, what's coming after GPUs, heterogeneous hardware like the M1 chips from Apple. And the plan is to release every 6 months with the GLVIS release coming 1 month after the MFEM release. Now here's the question for you. What would you like to see? These are some of the topics that I picked from the suggestions of the survey. So things like geometric preprocessing, better estimators, error estimators, meshes with elements of different topological dimensions, so line and inside a 2D mesh, or in addition to a 2D mesh. Parallel isotropic MR, support for 4D. We have some initial support for 4D, but if you want to do space-time, that might be important for you. So the best way to give us this feedback is today will be on the Slack channel. We have Meet the Team on the Slack workspace, sorry. We have a Meet the Team channel where you can go and grab the MFEM developers if you want to ask one-on-one questions or just provide feedback. That's the place to go. In general, the best place to get a hold of us is GitHub. As I said, our old development is there, so open an issue or discussion. And if you prefer email, we also have this email, mfem@lnl.gov. But that probably will be the slowest way to get feedback.